Have you ever noticed how some software just keeps working? Like really big systems, think Netflix, Amazon, those massive platforms, they roll out new features constantly, scale to millions of users seamlessly, and yet they rarely seem to collapse entirely, even if one tiny part has a hiccup. Contrast that with, say, an update that crashes your entire operating system or one bug in one corner of an app that brings the whole thing down. You know that feeling. Okay, let's unpack this. Today, we're diving deep into the architectural philosophy that makes that incredible resilience and agility possible. Microservices architecture. This isn't just some technical buzzword. It's really a strategic shift that's fundamentally changing how every piece of digital infrastructure, from your banking app to your favorite streaming service, is built and maintained.
Yeah, what's fascinating here is that we're truly witnessing a paradigm shift. I mean, for decades, applications were largely constructed as single, enormous, unified entities, what we affectionately call monoliths.
Right, the big block.
Exactly. Now, we're moving towards a decentralized, highly modular approach. So our mission in this deep dive is to not only explore what microservices are, but crucially, why they became necessary, the often underestimated complexities they introduce, and how leading organizations are securing them against some very real and evolving threats. We'll be extracting those vital nuggets of knowledge from our sources, in-depth reports, real-world case studies, and industry analyses to give you a shortcut to being truly well-informed.
So if you're looking to understand the core engine behind today's digital economy, and maybe even gain a competitive edge in how you think about building and managing complex systems, you're definitely in the right place. We're going to give you those surprising facts and deep insights you probably won't find just skimming headlines. Let's dig in. Setting the stage. The evolution of software architecture. Okay, so before we jump into this whole revolution, it's really crucial to understand what microservices are reacting against. Imagine a gleaming modern skyscraper. Now, imagine it was designed with every single system, plumbing, electricity, internet, elevators, all interwoven into one giant indivisible block. If the plumbing on the 20th floor sprang a leak, you might have to shut down water to the entire building. Worse, fixing it might require scaffolding the entire thing, risking the stability of the whole structure. That in essence, is the challenge of a monolithic application.
It's a perfect analogy, actually. A monolithic application is just that. A single consolidated unit. All its components, the user interface you interact with, the business logic that handles, everything from calculations to data processing, and the data access layer that talks to the database, they're all inextricably packaged together. And when you start a small project, this approach feels wonderfully simple. It really does. One code base, one deployment seems like rapid initial development.
Yeah, get you going fast.
Absolutely, can absolutely accelerate your initial time to market.
But here's where it gets really interesting and often quite painful. That initial simplicity, which is so appealing for a startup, right? It unravels dramatically as an application grows. Grows in size, complexity, and crucially, user base. What were once benefits quickly transform into major systemic headaches.
Yeah, this is where the rubber meets the road. So what are those inherent challenges that turn that early simplicity into long-term strategic and, operational burdens? First, there's complexity at scale. As your single code base grows, maybe to millions of lines, with hundreds of developers all touching it, it becomes incredibly unwieldy.
A tangled mess.
Exactly. Think of it as a single, sprawling spreadsheet where everyone is trying to make changes at the same time. It dramatically slows down development, makes it incredibly difficult to onboard new engineers, and significantly increases the risk of, unintended side effects with every minor change. Second, you've got deployment bottlenecks and inherent risk. If your application is one massive block, any change, no matter how tiny, even updating a logo or fixing a typo, requires you to rebuild, retest, and redeploy the entire application.
The whole thing, every time.
Every single time. This isn't just time-consuming, often taking hours, days even, but it's immensely risky. A single bug, a tiny flaw in one corner can, and believe me, often does, bring down the entire system, leads to widespread outages. We've all seen that frustrating system maintenance message, right?
Oh yeah, usually at the worst possible time.
Always. Third, there's inefficient resource utilization and scaling. Let's say you're running a massive e-commerce platform. During a flash sale, the shopping cart service gets absolutely hammered, but maybe the user profile or recommendations engine isn't under much extra load at all.
Right.
In a monolithic architecture, to handle that shopping cart surge, you're forced to scale the entire application. You're spinning up extra servers, memory, CPU for components that don't need it. That leads to significant and often wasteful costs.
Paying for resources you're not using for most of the app.
Precisely. And finally, technology lock-in. When everything is tightly coupled within a single technological stack, maybe it's all Java or all Python, with one specific database, adopting new technologies becomes an enormous undertaking. If you want to leverage a newer, more efficient programming language or database for a specific problem, you're looking at potentially rewriting a substantial, if not the entire, portion of your application. That's a massive barrier to innovation.
So that short-term win of simplicity effectively becomes long-term technical debt and operational burdens. It feels like a Faustian bargain. Speed now, pain later. This fundamental trade-off really pushed the industry, I guess, to look for something different, a better way. Okay, now let's take that skyscraper analogy and let's transform it. Imagine instead a dynamic city skyline. Each building is a distinct entity with a single purpose. One is a residential tower, another a power station, another a library. Each has its own dedicated team maintaining it, its own specialized infrastructure, and crucially, can be upgraded, renovated, or even completely rebuilt without affecting the others. That's a much closer picture of microservices, right?
Indeed. That's a great way to put it. A microservices architecture is essentially a style of developing applications as a collection of smaller, independent, and loosely coupled services. Each one is a self-contained unit boasting its own codebase, its own business logic, and often, critically, its own dedicated data store. They're built to accommodate a very specific feature or business capability, and these services, they communicate not through tight internal code dependencies like in a monolith, but through lightweight, well-defined APIs, typically over a network. This modularity is a direct response to those scalability and agility challenges inherent in monoliths.
So what really defines this new paradigm for you? Like, what are the non-negotiable elements that make a microservice architecture truly effective? What makes it work?
Okay, there are three pillars that come to mind immediately for me. The first is autonomy. Each service can be developed, deployed, operated, and scaled entirely independently. This is massive. Think about it. A team responsible for a payment service can push an update without coordinating a huge system-wide deployment that dramatically accelerates release cycles. It's the cornerstone, really.
Total independence.
Well, independence in its life cycle. The second is specialization, often guided by the single responsibility principle. A microservice should do one thing and do it well. Think of it as a highly skilled specialist. In an e-commerce platform, you don't have one sprawling user service. Instead, you'd likely have a user authentication service, a user profile management service, and maybe an order history service. Each is cohesive, easier to understand, maintain, and scale because its scope is so focused.
Keeps things clean.
Exactly. And third, independent deployability. Each microservice is its own deployable unit, typically packaged up as a container, like Docker, with its own source control and its own CI/CD pipeline. This means you can update a single feature without impacting or redeploying the rest of the application. It's the practical manifestation of that autonomy we talked about. Now, if we connect this to the bigger picture, it's absolutely vital to grasp that while these services are independent in their life cycle, how they're built and deployed, they are profoundly interdependent in their function.
Oh.
A single user request, like checking out a shopping cart, might involve calls to a dozen different microservices. Inventory, payment, shipping, notifications, you name it. The magic, and honestly the challenge, is managing this sophisticated dance to ensure a cohesive user experience.
That paradox of independence and interdependency seems like the central tension of microservices, doesn't it? How does it manifest in the day-to-day work, and what are the first principles you need to keep in mind to manage it? Maybe to solidify this, let's quickly stack these two architectural styles against each other, point by point.
Good idea.
For scalability, monoliths force you to scale the entire application, like upgrading the entire road network for just one busy intersection.
Right. Wasteful.
Whereas microservices let you scale each service independently. If your payment service is swamped, you only scale that service. Much more flexible, much more cost-effective.
Absolutely. Targeted scaling.
In terms of reliability, a bug in one part of a monolith can bring down everything. One bad apple spoils the whole barrel.
Yep. The whole system goes dark.
Microservices, because they're compartmentalized, they isolate faults. A failure in the recommendation engine doesn't crash the entire e-commerce site. It might just mean recommendations aren't shown for a bit. It's like a graceful degradation.
Exactly. Containment.
When it comes to deployment, monoliths require redeploying the entire application for any change, which is slow and high risk.
The dreaded weekend deployment window.
Microservices are independently deployable, enabling faster and more frequent releases. You hear about companies doing multiple times a day.
Continuous delivery becomes achievable.
For technology, monoliths are often constrained by a single, maybe aging tech stack.
Stuck with decisions made years ago.
Microservices, conversely, allow teams the freedom to choose the best technology for each specific service. This polyglot development, as they call it, empowers teams to use the right tool for the job.
Yeah, use Node.js here, Java there, Python over here, whatever fits best.
And finally, teams. Monoliths often lead to large siloed teams specializing in layers, like front-end team, back-end team, database team.
Lots of handoffs, slow communication.
Microservices tend to foster small, cross-functional teams organized around specific business domains or capabilities. This increases ownership and really accelerates productivity.
Right, the two-pizza team idea, owning a service end-to-end. So it's clear the decision to adopt microservices isn't just a technical preference. It's often a profound strategic imperative for many organizations. It's really driven by core business needs and the relentless demand for competitive advantage in our, hyper-digital world.
So why are companies truly making this fun and, let's be honest, often very expensive shift? What are the strategic gains they're really aiming for?
Well, two big ones jump out.
Okay.
Firstly, faster time to market. Monoliths simply cannot keep pace with the rapid iteration and deployment cycles needed today. Microservices allow organizations to innovate and get products and features into users' hands significantly faster. We've seen companies reduce their release cycles from months down to days or even hours after migrating.
That's huge.
It is, and closely tied to that is greater agility. Companies need to respond to shifting market demands, new customer expectations, or competitive threats with incredible speed. Microservices empower these small, autonomous teams to work independently, adapt to new requirements swiftly, and pivot much faster than a cumbersome monolithic structure ever could. It's really about being nimble in a fast-moving world.
So it's about speed and flexibility at a business level.
Exactly. This architecture provides the foundational flexibility and resilience demanded by modern, large-scale applications, think e-commerce giants, streaming platforms with global audiences, or high-frequency financial services. These are industries that experience fluctuating, often massive user demands and require exceptionally high availability. It's not just about what the technology can do, but what the business needs to do to survive and thrive in today's landscape. 2. Foundational principles. The blueprint for success.
Okay, so this isn't just about breaking things into smaller pieces randomly, though. That sounds like chaos. There's got to be a method to the madness, right? A thoughtful design philosophy guiding this decomposition. You mentioned it starts with something called domain-driven design, or DDD.
Indeed, yes. Microservices are not about chaotic fragmentation. They should be a deliberate structuring of services around specific business capabilities, and the core idea of DDD is precisely that. To align your system's technical design directly with the underlying business logic and requirements. So each microservice focuses on a specific business domain. Imagine a ride-sharing app. Instead of one amorphous app service, you'd meticulously design, say, a ride services microservice, a driver management microservice, and a payment processing microservice. This clarity promotes clear boundaries and helps teams understand their precise scope.
Prevents scope creep within the service itself.
Exactly. Without DDD, you risk developers creating services that try to do too much, and they essentially become mini monoliths themselves, defeating the purpose.
And what's fascinating here is this concept of a bounded context. It sounds a bit academic, but it feels incredibly practical for keeping things clean and organized.
It's a truly crucial element of DDD, maybe the most crucial. Each microservice operates within a bounded context, which is a clearly defined logical boundary within the larger business domain. And inside that boundary, a specific term or concept holds a consistent, unambiguous meaning.
Can you give an example?
Sure. Think about the word customer. In a sales context, within that bounded context, customer might refer to a potential lead you want to acquire with associated CRM data. But that same customer in a support context might be someone needing assistance with ticket history and communication logs. The bounded context ensures that within its boundaries, say within the sales microservice or the support microservice, the term customer has a single, clear definition. This drastically minimizes overlap and misunderstanding between services and teams. It leads to each service having that single, well-defined purpose.
Ah, so it prevents confusion across different parts of the business reflected in the code.
Precisely. And this alignment profoundly improves collaboration as teams explicitly own their piece of the business domain, effectively blurring the lines between technical decisions and core business strategy. It connects the code directly to the business need.
Okay, and we touched on this earlier, but it seems so critical to the philosophy of microservices that it bears repeating. The single responsibility principle, or SRP.
Absolutely, it's fundamental. This principle mandates that a microservice should have one and only one reason to change. It should focus exclusively on a specific business capability or a clearly defined subdomain. To use our authentication microservice example again, it should handle only authentication logic. Login, logout, token validation, maybe password resets. It wouldn't concern itself with managing user profiles or order history. Its API, its interface would expose only those functions relevant to authentication.
Which makes it super easy to understand and maintain, I guess.
Exactly. It makes it incredibly easy to understand, test, and maintain because its scope is so limited and focused.
And that focused responsibility leads directly to something you mentioned called high functional cohesion. That sounds like the secret sauce for clean, maintainable code in this world.
That's right. It's a key outcome. High functional cohesion means all the logic and all the data related to that service's single concern are entirely encapsulated within its deployment unit. Everything the authentication service needs is right there, and importantly, nothing it doesn't need is. This cohesive design is what directly enables loose coupling, which is paramount in microservices. It minimizes a service's internal dependencies on other services. If you need to change how authentication works, you only touch that one authentication service.
You don't risk breaking something totally unrelated.
Exactly. You don't have to worry about accidentally breaking the payment system or the inventory system because their code and data are completely separate. This relationship, high cohesion enabling loose coupling, is precisely what unlocks the key benefits of microservices, like that independent deployment and the flexible scalability we talked about. 3. Unlocking business value. The benefits of microservices.
Okay, let's talk more about those benefits. One of the most important and often the most visible advantages here is the ability to scale each component independently. This seems like a huge win when you compare it to the all-or-nothing approach of monoliths.
Absolutely. Think back to our holiday shopping example. In a monolithic system, if there's a massive surge in demand for, say, the product recommendation engine during a big sale, you'd be forced to scale the entire application, every single component, regardless of whether it's under load or not.
Right, spinning up huge servers for everything.
Exactly. With microservices, you only need to scale up the recommendation service itself. This granular, independent scaling allows for much more flexible and crucially efficient resource utilization. One company we studied reported something like a 30% reduction in their infrastructure costs just by eliminating that over-provisioning for low-demand services after they migrated to microservices. It enables organizations to right-size their infrastructure precisely where it's needed.
Which leads to significant cost efficiencies, and you could even more accurately measure the cost of a specific feature.
Precisely. That kind of granular cost tracking becomes possible.
Now, this is where the compartmentalized nature of microservices really shines in improving a system's resilience. The idea that if one service fails, it doesn't take down the whole house of cards.
Indeed, that's a massive advantage. If, for instance, a third-party payment gateway integration service on an e-commerce platform encounters an issue or goes offline temporarily.
Which happens.
Which definitely happens. The rest of the platform can continue to function. Users might be temporarily unable to complete purchases through that specific gateway, but they can still browse products, add items to their cart, maybe check their order status, and perhaps even pay with an alternative method if one is available. The system might gracefully degrade that specific functionality rather than crashing the entire application. This fault isolation is a powerful advantage over monolithic systems, where a single component failure could lead to catastrophic system-wide outages. It prevents a localized problem from becoming a global crisis.
But this isn't magic. You have to actually design for this resilience, right? It doesn't just happen automatically because you're using microservices.
Exactly. That's a critical point. The ability to gracefully handle service failures is a deliberate design consideration. It has to be built in. The circuit breaker pattern is a key technical response to this requirement.
Like in your house's electrical panel?
Precisely like that. It prevents a service from repeatedly trying an operation that is likely to fail anyway. If a dependent service becomes unresponsive or starts throwing errors, the circuit breaker trips. It immediately fails any further calls to that service for a period, preventing the calling service from wasting resources or experiencing long, cascading timeouts.
So it stops the problem from spreading.
Exactly. By proactively failing fast and preventing those cascading issues, this pattern ensures the system remains operational and stable overall, even if a dependent service temporarily goes offline. It's a vital tool for building robust distributed systems. You absolutely need patterns like this.
Okay, let's talk speed again. Everyone wants to get their product or feature to market faster, especially in today's rapid-fire digital economy. Microservices definitely seem to deliver here.
They absolutely do. The independent deployability of microservices enables significantly faster and more frequent release cycles. It's a direct consequence. Unlike a monolith, where even a minor code change necessitates redeploying the entire, often massive, application or process that can take hours or days and involve significant risk.
Yeah, the big weekend release cycle.
Right. Microservices allow teams to deploy updates or fixes to individual services with minimal disruption to the overall system. This decoupling dramatically enhances agility, empowering teams to swiftly roll out new features, bug fixes, or performance improvements. This directly accelerates time to market. Imagine deploying 50 times a day instead of once a month. That's the kind of game changer we're talking about for competitive advantage.
It also sounds like it significantly lowers the stakes of trying new things.
Uh-huh.
If a small change to one service doesn't jeopardize the whole application, you're probably more likely to experiment, right?
Precisely. That's a huge cultural benefit, too. The ability to deploy independently significantly lowers the cost of failure. If an experiment with a new feature in one service doesn't pan out or introduces a bug,
You just roll back that one service.
exactly. It's much easier to roll back or iterate on just that service rather than having to undo a massive, complex, system-wide change. This empowers teams to experiment more freely with new ideas and iterate quickly based on feedback. The resulting shortened development cycle times, combined with this increased experimentation, lead to a significant aggregate throughput for the entire organization. More value delivered faster. It really fosters a culture of innovation, not fear of breaking things.
Now, this organizational benefit often gets overlooked, I think. We tend to focus on the cool tech advantages, but it's hugely impactful. It's really about how people work together, or independently.
It truly is. A microservices architecture naturally fosters, or maybe demands, a culture of small, independent, and autonomous teams that take clear ownership of their specific services. Imagine a team of, say, 5 developers being fully responsible for the payment processing service from its initial concept all the way through to development, deployment, operation, and ongoing maintenance. This you build it, you run it mentality gives team members a much deeper sense of ownership, expertise, and accountability.
Cuts down on the blame game and handoffs.
Absolutely. It cuts down handoffs, bureaucratic approval processes, and that classic not my problem syndrome you see in larger layered teams.
And what does that structure mean for overall productivity and the speed at which new features actually arrive? Less waiting around, I'd imagine.
It's a massive game changer for productivity. This structure enables multiple teams to work in parallel on different services without constantly stepping on each other's toes, waiting for bottlenecked shared resources, or getting lost navigating massive monolithic code bases. This parallelization significantly increases developer productivity and directly accelerates the delivery of new features. The clear boundaries and the well-defined service APIs also promote better collaboration, paradoxically. Each team knows exactly what its service is responsible for, how it exposes its functionality, and how it interacts with others. It actually streamlines communication and reduces coordination overhead.
Leads to happier, more productive engineers, hopefully.
That's the goal. Less friction, more flow. 4. The technical fabric, making microservices work.
Okay, so we have all these independent services, each doing its own thing, often with its own database. But for the application to function as a coherent whole, they obviously need to interact, they need to talk to each other. How do they do that? What's the actual conversation like in a microservices world?
That's a critical question, and honestly, it's where much of the technical complexity and the really important design decisions lie. Microservices communicate primarily using 2 distinct patterns, synchronous and asynchronous. And the choice you make for any given interaction is a critical architectural decision. Each has significant trade-offs that impact performance, resilience, and complexity.
Okay, let's unpack synchronous communication first. That sounds like a direct, immediate interaction, maybe much like a function call within a monolith,
Yeah.
but now it's happening over a network.
Yes, exactly. Synchronous communication is a lot like making a direct phone call. When one service, let's call it the client, needs information or a specific action from another service, it calls an API exposed by that other service, and then it waits for an immediate response. The client service is effectively blocked, unable to proceed with its own work until it receives a reply or until a predefined timeout occurs. You're likely familiar with common protocols like HTTP REST for this kind of thing.
Yeah, standard web APIs.
Right. But gRPC is also gaining significant traction, especially for high-performance internal communication between services. Now, while this pattern is relatively straightforward to implement and often easier to debug because of its direct request-response flow,
You know, if it worked or failed right away.
you do, but it creates tight coupling at runtime. The calling service directly depends on the immediate availability and performance of the receiving service. If the receiving service is slow or unavailable, the calling service is also impacted. It has to wait. This can lead to performance bottlenecks and, worse, cascading failures if a whole chain of synchronous calls gets backed up.
Right, one slow service slows down everyone calling it.
Precisely.
Okay, so what about asynchronous communication? That sounds a bit more hands-off, perhaps less immediate, but maybe more resilient. Is it more like sending an email and expecting a reply at some point rather than a phone call?
That's a great analogy, yes. Asynchronous communication is much more like sending an email or maybe dropping a letter in the mail. A service sends a message without waiting for an immediate response. Instead, it typically places this message into an intermediary, usually a message broker. Think systems like Apache Kafka or RabbitMQ. The sending service then immediately moves on to other tasks. It doesn't wait.
Fire and forget.
Exactly, fire and forget. The message broker holds onto the message reliably until another service, the consumer, is ready to pick it up and process it at its own pace. This approach is fantastic for promoting loose coupling, as the sender doesn't need to know anything about the consumer or even if the consumer is currently available or running. It also greatly improves resilience because messages aren't lost if the consumer is temporarily down. They just get processed when the consumer recovers. However,
There's always a however.
there is. It introduces more complexity to implement, and especially to debug, because you no longer have that direct call and response flow. Tracking a message through the system can be harder, and it often leads to that state we call eventual consistency.
Okay, eventual consistency. That sounds like a critical concept and maybe a major mental shift for developers used to traditional databases where everything is instantly consistent.
It absolutely is. With asynchronous communication, data updates might propagate through the system over time. This means that different parts of the system might not immediately see the absolute latest state of the data. For example, an order might be confirmed to the user instantly by the ordering service, but the inventory count might update a few milliseconds or maybe even seconds later in a separate inventory service that consumed an event.
So things are slightly out of sync for a short time.
Potentially, yes. And while this is perfectly acceptable, even desirable for many scenarios, it needs careful handling. It can significantly complicate debugging if you're looking at different states of data in different services at the same moment. It also requires a different approach to querying data that logically resides in multiple services. You often see patterns like CQRS, Command Query Responsibility Segregation, used here. This pattern separates the models you use for updating data, the commands, from the models you use for reading data, the queries. You might create a specific read-optimized replica of data gathered from one or more services, specifically for complex queries, even understanding that this replica might be eventually consistent.
So you build specialized views for reading.
Essentially, yes. This represents a fundamental shift from a centralized, single source of truth database model to a highly distributed one. It truly requires advanced design patterns and a new mindset to ensure data integrity and usability across the entire system. And just to wrap this point, a successful microservices system rarely uses just one communication pattern. It almost always employs a strategic mix of both. Synchronous calls for those immediate, real-time interactions where tight coupling is acceptable or necessary, and asynchronous messaging for decoupled, long-running processes or events where immediate feedback isn't crucial, prioritizing resilience and scalability.
Okay, that makes sense. Now, in this dynamic environment where services are constantly scaling up or down based on load,
Yeah.
and their network locations, their actual IP addresses and ports are changing all the time, potentially minute by minute, how does one service even find another service to communicate with it? You can't just hard code an address in a configuration file, right? Because that address might be gone or changed in the next deployment.
That's precisely the core challenge that service discovery solves, and it's absolutely fundamental to making microservices workable at any kind of scale. Service discovery is the process or mechanism by which components in a distributed system locate and communicate with each other dynamically without prior knowledge of their exact network location. It typically relies on a central component called a service registry. This registry keeps a global, usually highly available, and up-to-date record of all active microservices network locations, their addresses, ports, maybe some metadata, and even their current health status.
So it's like a dynamic phone book for all the services, constantly updating itself automatically. A bit like having a constantly refreshed, self-managing directory of every person's current whereabouts and whether they're available to talk.
Exactly. That's a perfect analogy. When a microservice instance starts up, one of the first things it does is register its location and details with the central registry. Then, when a client service needs to talk to another specific service, say the payment service, instead of needing to know its exact address.
It just asks the phone book.
Right. It simply queries the service registry, saying, hey, give me the location of a healthy instance of the payment service. The registry then returns the network location of a currently available and healthy instance, and the client can make its direct call synchronous or send its message asynchronous to that location. This mechanism completely eliminates the need for fragile, hard-coded configurations, which, as you pointed out, would be an absolute nightmare to manage and maintain in a dynamic cloud environment with auto-scaling and frequent deployments. It's a critical component. It effectively addresses that paradox of autonomy and interdependency by providing a centralized, dynamic way for independent services to find each other and collaborate seamlessly. Without effective service discovery, your microservices wouldn't even be able to have those phone calls or send those emails we talked about.
Got it. Now, a key advantage, maybe the key advantage of microservices is their independent deployability. You can update one service without touching others. But how do organizations actually maximize this benefit while simultaneously minimizing the risk and downtime for users? This sounds like a high-wire act, deploying constantly without breaking things.
It absolutely can be, and that's where modern deployment strategies really come into play. These are heavily enabled by those powerful containerization tools like Docker and sophisticated container orchestration platforms like Kubernetes. These technologies really form the bedrock of modern microservices deployment pipelines. Let's start with containerization and orchestration. Containers, most famously Docker these days, have become the de facto standard choice for packaging microservices. They bundle a service together with all its dependencies, its code, runtime environment, system tools, libraries into a single, isolated, and portable unit.
Everything it needs to run, all in one box.
Exactly. This ensures that each microservice operates autonomously and, crucially, consistently across different environments, development, testing, production. It finally solves those old, well, it works on my machine problems. Then you have container orchestration tools, with Kubernetes being the dominant player now. These tools automate the entire lifecycle management of these containers at scale. Kubernetes handles everything from deploying new instances of your services, automatically scaling them up or down based on demand, load balancing traffic across healthy instances, and even managing things like service discovery and resource allocation for potentially hundreds or thousands of containers.
It's like having a hyper-efficient air traffic controller for all your running services.
That's a great analogy. It manages the fleet. Now, building on this foundation of containers and orchestration, we have several advanced deployment strategies designed specifically to ensure high availability and minimize risk during updates. First, there's blue-green deployment. Imagine you have two identical production environments. Let's call them blue and green. The blue environment is currently serving all your live user traffic. When you have a new version of your service ready,
You deploy it to the green environment first.
right, you deploy it completely to the green environment, which isn't receiving live traffic yet. You test it thoroughly there, run smoke tests, integration tests, whatever you need. Once you're confident it's working perfectly, you instantly switch all incoming traffic, usually at the load balancer or API gateway level, from blue to green.
So the switch is instantaneous.
Pretty much. Benefits. This provides true zero downtime deployments because you're switching between fully functional environments. It also allows for instant and easy rollbacks. If any unforeseen issues emerge in green after the switch, you just switch the traffic right back to blue immediately.
What are the downsides? Sounds pretty good.
Pitfalls. The main downside is cost and complexity. It requires you to have essentially double the infrastructure running simultaneously, at least during the deployment window, which can significantly increase costs and operational complexity to manage. There's also the potential for subtle version mismatch issues if you're deploying multiple interdependent microservices using blue-green at slightly different times, requiring careful coordination. Next up, canary deployment. This strategy is famously named after the canary in a coal mine, testing the waters carefully. You release a new version of a service, the canary, to only a small, isolated percentage of your users or servers first. Maybe just 1% or 5% of traffic goes to the new version.
So most users still get the old stable version.
Exactly. This limited exposure allows you to rigorously monitor the new version for any issues, errors, latency spikes, unexpected behavior before it impacts a wider audience. If the canary metaphorically croaks, you roll it back quickly, affecting only that small group. If it sings and performs well,
You gradually increase the traffic.
right, you gradually roll it out to more users, maybe 10%, 50%, then
100%
100% benefits. It detects problems early with a very limited user set, significantly reducing the risk of widespread failures. It allows for a phased, controlled transition to the new version based on real-world performance data.
And pitfalls.
Pitfalls. You absolutely need robust, real-time monitoring and alerting in place to catch those early issues in the canary group. Otherwise, you're flying blind. Also, if you're deploying microservices very frequently or without adequate pre-release testing, even canary releases can introduce issues, potentially slowing down overall development velocity if not managed carefully with good automation and rollback procedures. Finally, there's rolling deployment. This is perhaps the most common and often the default approach in many orchestrated environments like Kubernetes. The new version of a service is incrementally deployed one instance, or a small batch of instances at a time, gradually replacing the old version while other instances remain running and continue to serve traffic.
So you replace them piece by piece.
Exactly. Maybe you have 10 instances running. You take down one old one, bring up one new one, wait for it to be healthy, then repeat for the next one, and so on.
Benefits seem clear, less downtime.
Benefits. This strategy effectively reduces downtime and the risk of widespread failures, as only a small portion of your instances are being updated at any given moment. It provides continuous availability throughout the deployment process.
And the catch.
Pitfalls. Similar to Canary, it requires continuous and active monitoring to detect issues as they arise during the incremental update process. If a problem is introduced in the new version, it might affect a subset of users hitting the newly updated instances before the rollout is automatically paused or manually stopped. So immediate detection and automated rollback capabilities are really key to making rolling deployments safe. Navigating the complexities. The double-edged sword.
Okay, so far, microservices sound almost like a silver bullet, solving pretty much every problem monoliths created. But as we know, in tech, there's rarely a free lunch. With great power comes, well, a new class of complexities and challenges. It's definitely a double-edged sword that can cut both ways if you're not careful.
You're absolutely right. It's crucial to have a balanced view. The flexibility and autonomy of microservices, while incredibly powerful, introduce significant operational complexity and can indeed increase maintenance costs if not managed meticulously. Unlike a monolithic system with usually a single point of management and troubleshooting, a microservices application involves multiple code bases, multiple deployment units, multiple databases potentially, and each one has its own independent lifecycle. Imagine managing not just one skyscraper, but maybe 1,000 small, interconnected buildings, each with its own unique quirks and maintenance schedule.
That sounds exhausting.
It can be. This demands an incredibly high level of coordination, sophisticated tooling, and very clear separation of responsibilities between teams, which is a new organizational challenge in itself.
What's genuinely surprising to me, sometimes, is how often what looks like a win for efficiency, like team autonomy, can paradoxically lead to a loss of overall operational leverage, if not managed correctly. Instead of one big thing to manage, you suddenly have hundreds or thousands of little things.
Absolutely. That's a key insight. Without rigorous operational discipline and a mature DevOps culture underpinning it all, you can quickly end up with a sprawling, complex, and often poorly documented technical stack spread across dozens or hundreds of services. Different teams using different libraries, different monitoring tools, different deployment practices. It can become chaos. And this isn't just a technical problem. It results in ballooning technical costs as you try to manage the sheer volume and diversity. You might even need additional layers of management bureaucracy just to coordinate the distributed teams and their independent efforts. In essence, the distributed nature can replace the single, albeit unwieldy, problem of the monolith with a whole new and sometimes even more difficult set of problems related to managing this highly complex web of interconnected services. Some industry reports even suggest that organizations with immature microservices adoption, those who jumped in without the right foundation, can actually experience higher failure rates and slower initial productivity compared to when they were on their monolith.
Wow, so it's not a guaranteed win.
Definitely not. It's a journey that requires significant, often painful, investment in operational maturity, automation, and tooling.
Okay, let's talk about data. This feels like a really big one. If each service ideally has its own dedicated database, which is a core tenet of microservices for achieving that loose coupling, how on earth do you keep everything consistent across the system, especially when a single business transaction needs to span across multiple services? For example, placing an order might involve deducting inventory in one service, processing a payment in another, and updating the user's order history in a third. How do you make sure all those happen reliably, or none of them happen?
This is indeed a core challenge, and probably one of the most significant architectural trade-offs you make when you move to microservices. Traditional database mechanisms like distributed transactions using two-phase commit protocols, which aim to ensure atomicity across multiple resources.
Like in a single database.
Right. Those are rarely viable or performant for distributed transactions in microservices. They tend to introduce tight coupling between services, everyone has to agree to commit or roll back, and significant latency, hurting availability. A common and much more pragmatic solution in the microservices world is the Saga pattern. This pattern orchestrates a sequence of local transactions across multiple services. Each local transaction updates data only within a single service, and then, upon success, it publishes an event or sends a message to trigger the next transaction in the sequence.
So it's a chain reaction of local updates.
Exactly. And if any step in the sequence fails, the Saga pattern defines compensating transactions that are executed to undo the actions of the preceding successful steps, effectively maintaining business consistency, albeit not atomic consistency in the traditional sense.
That sounds complex to manage and debug if something goes wrong halfway through.
It absolutely is. The real challenge with sagas isn't just orchestrating the forward steps, but effectively implementing, visualizing, and debugging the compensating transactions when a failure occurs across potentially dozens of services. It requires careful design and robust tooling.
This reliance on events and messages often leads directly back to something we mentioned earlier, eventual consistency. It sounds like data isn't always perfectly in sync in real time, which again can be a tricky concept for people used to traditional databases.
That's right, and it's a fundamental mental shift you have to make. The reliance on asynchronous communication and event-driven patterns like sagas, which are so crucial for loose coupling and resilience, often leads to this state of eventual consistency. This means that data updates propagate through the system over time, rather than being immediately consistent across all services the instant a transaction completes. Like our order example. The order might be confirmed to the user instantly, but the inventory count reflecting that order might update a few milliseconds or maybe even seconds later in a separate inventory service that eventually processes the order-placed event.
So for a brief window, the inventory count might be slightly inaccurate if queried directly.
Potentially, yes. While this is acceptable, even desirable, for many business scenarios, like showing an estimated inventory level, it can significantly complicate debugging because you might be looking at different states of data in different services at the exact same moment. It also requires a different approach to querying data that logically resides in multiple services. How do you get a unified view? The CQRS, Command Query Responsibility Segregation pattern, is often employed here to help. With CQRS, you explicitly separate the models and data stores used for updating data, the commands, from the models and data stores used for reading data, the queries. You might create a dedicated read-optimized data store, a read model or view model, that aggregates data from one or more microservices, specifically tailored for complex querying needs. This read model is updated asynchronously based on events from the source services, meaning it's eventually consistent.
So you build specialized views optimized for reading, accepting that they might be slightly delayed.
Essentially, yes. It acknowledges and embraces eventual consistency for read operations. This represents a fundamental shift from that centralized, single source of truth database model to a highly distributed one. It truly requires advanced design patterns, careful consideration of consistency requirements, and a new way of thinking to ensure data integrity and usability across the entire distributed system.
Okay, beyond just the tricky data consistency issues, microservices also introduce other forms of overhead that can impact performance and operability.
Yeah.
It's not just about what you gain in flexibility, but what new challenges you take on in terms of system performance and management.
Correct. The very nature of inter-service communication, even if it's fast, means that every single call between two services incurs some additional network overhead and can introduce latency compared to an in-process call within a monolith. Even if each individual network hop is quick, maybe just a few milliseconds, when a single user request fans out to call 10, 20, or even more different microservices to assemble the final response, that latency can compound significantly. It can lead to a slower overall response time for the end user if not managed carefully. This requires careful performance tuning, efficient communication protocols like gRPC perhaps, and maybe caching strategies.
And what about debugging? That sounds like a nightmare.
It can be significantly more challenging, yes. In a monolith, if something goes wrong, you often have a single application log, maybe on a single server, to pore over. You can trace the execution flow relatively easily. In a microservices environment, a single business process, like that order placement, can run across many different services, each potentially running on different servers or containers, each generating its own set of logs. Trying to trace a single user request end-to-end through this distributed maze and pinpoint the root cause of a failure, well, it's incredibly difficult and time-consuming without specialized
You
tools.
need better tools.
Absolutely essential. You need centralized logging platforms, think Splunk, Elasticsearch, Log/Kibana, the ELK stack, Datadog logs, to aggregate all the logs in one place. And critically, you need distributed tracing tool systems like Zipkin, Jaeger, or OpenTelemetry integrated tools that can track a request with a unique ID as it hops between services, visualizing the entire call chain and pinpointing where delays or errors occurred. The complexity of testing also increases substantially. Integration testing requires orchestrating interactions across various interconnected services, often needing a specialized, complex test environment that mimics production. It's far more involved than testing a single unified application. It's like trying to find a single faulty light bulb, not just in one house, but across an entire city where every building has its own unique electrical system and blueprint. Securing microservices, expanded attack surfaces.
Okay, let's shift gears to security. We've got all these independent services communicating, often across a network, each potentially exposing its own API, maybe connecting to its own database. The attack surface, the number of potential points an attacker could target, seems absolutely massive compared to a single monolith. How do you even begin to protect something so distributed effectively?
You've hit on a critical point, probably one of the biggest challenges. The distributed nature of microservices fundamentally expands the security attack surface. It creates far more potential entry points for malicious actors. Each service API, each network connection, each data store is a potential target. This means security cannot, absolutely cannot, be an afterthought bolted on at the end. It must be integrated right from the design phase with a proactive, multi-layered approach. And a truly crucial component in establishing a strong microservices security posture right at the front door is the API gateway. The API gateway acts as a single, centralized entry point for all or most external client requests. It sits in front of your microservices and carefully routes incoming requests to the appropriate backend service.
So it's like a strategic security barrier, maybe like a bouncer at the front door of your entire application cluster before anyone gets into the party. It sounds like it consolidates a lot of initial security checks in one place.
Exactly. It's a highly strategic security barrier, almost like a castle's well-guarded gatehouse protecting its inner keep. The API gateway shields the underlying microservices from direct exposure to the potentially hostile outside world, making them much harder for attackers to discover and compromise directly. This centralized approach also allows the API gateway to offload several critical security functions from the individual services themselves, rather than having each service team try to implement and potentially misimplement them on their own. These functions typically include authentication. The API gateway can validate user credentials, like checking JWT tokens or API keys, for all incoming API requests. This centralizes the authentication process, ensuring consistency and minimizing security gaps that could easily arise if each of the dozens or hundreds of services managed its own authentication logic.
One place to get it right.
Exactly. Rate limiting and throttling. The gateway can control the number of API requests allowed from a specific client or IP address within a certain time period. This is absolutely essential for preventing various types of attacks, such as denial of service, DOS attacks, which try to overwhelm a service with excessive traffic, and also brute force attacks attempting to guess passwords or tokens, and policy enforcement. The gateway can enforce broader security policies and rules related to authentication, authorization, who is allowed to do what, and access control right at the edge of your system before a request even reaches a microservice. This ensures that only authorized clients and authenticated users can access specific microservices or specific API endpoints, acting as a crucial first line of defense. It's truly a strategic choke point for applying security consistently.
Okay, that makes sense for handling external traffic coming into the system, the north-south communication, as it's sometimes called. But what about the communication between the services themselves once a request is passed through the API gateway? That internal east-west traffic seems potentially even more vulnerable because it's happening behind the initial firewall, within what might be considered a trusted network zone.
That's a very perceptive point, and you're right. Securing this internal or east-west communication is absolutely as critical as securing the external traffic, if not more so. Internal services often have higher, more trusted privileges, so compromising one could allow an attacker to move laterally. A highly recommended best practice here, becoming increasingly standard, is mutual TLS, MTLS. Unlike regular TLS, which you see as the S in HTTPS in your browser, where typically only the server authenticates itself to the client using a certificate.
To prove it's the real website.
Right. MTLS requires both the client service and the server service to authenticate each other's identities using cryptographic certificates before establishing a secure connection. It's like both people showing verified ID before they start talking. This bidirectional authentication ensures that only trusted, authenticated services can communicate with each other significantly. That's where modern tools, specifically service meshes, come to the rescue. Yes, technologies like service meshes, Istio, and Linkerd are popular examples, can largely automate the implementation and management of MTLS across your entire fleet of microservices. The service mesh typically injects a small proxy container, like Envoy, alongside each microservice instance. These proxies intercept all incoming and outgoing traffic for the service. The mesh control plane then handles the complex tasks of certificate issuance, automatic rotation, and enforcing policies that require MTLS for communication between specific services. It abstracts much of the security complexity away from the individual service teams.
So developers can focus on business logic, not PKI infrastructure.
Exactly. It allows developers to focus on building features, knowing that the inter-service communication is automatically secured by the mesh infrastructure underneath. It's a huge operational advantage for security at scale.
Okay, let's talk secrets. Services constantly need things like database passwords, API keys for third-party services, authentication tokens, encryption keys, generically called secrets, just to function and talk to other resources. How do you manage those sensitive credentials securely in such a highly distributed environment where dozens or hundreds of services might need access to different sets of secrets? This seems like a massive potential vulnerability, if not done correctly.
This is an absolutely critical area and, frankly, a common source of major breaches if handled improperly. The improper management of secrets, particularly practices like hard-coding them directly into source codes, scripts, environment variables, or configuration files, is unfortunately still common and extremely dangerous. It can easily expose sensitive credentials to attackers if those files are accidentally checked into source control, logged, or otherwise compromised.
The Uber breach example comes to mind.
Exactly, a prime example. A centralized secrets management solution is essential to mitigate this risk. These are dedicated platforms. Popular ones include HashiCorp Vault, AWS Secrets Manager, Azure Key Vault, Google Secret Manager, designed specifically to securely store, transmit, and importantly, automatically rotate these credentials. They provide a single, secure source of truth for all secrets. Services authenticate to the Secrets Manager to retrieve the credentials they need, often just in time. And critically, these platforms provide a detailed audit trail of who or what accessed which secret and when. This approach prevents hard-coded credentials and significantly reduces the risk of breaches caused by compromised secrets. It's like moving from leaving your house keys under the doormat to storing them in a bank's high-security vault with access logs.
And this connects directly to a core fundamental security tenet that should apply universally, not just in microservices, right? The idea of minimizing permissions.
It's a direct and powerful application of the principle of least privilege. This fundamental security concept dictates that any user, or in this context, any service or application component, should only be granted the absolute minimum privileges necessary to perform its specific intended function and absolutely nothing more. By severely limiting a service's access, its permissions to read-write data, call other APIs, access system resources to only what it explicitly needs to do its job, the potential damage from a breach or a compromise of that service is dramatically minimized. If an attacker manages to gain access to one service, its limited permissions will restrict what they can actually do next and how far they can potentially move laterally within your system. It effectively contains the blast radius of any security incident.
It's about damage control built into the design from the start.
Precisely. It's about assuming breach will happen eventually and limiting the fallout when it does.
So putting this all together, given this expanded attack surface and all these moving parts, security truly can't be an afterthought, something you sprinkle on at the end. It has to be baked in from the ground up, right from day one of designing a service.
Precisely. That's the key takeaway for security and microservices. With the expanded attack surface and the inherent complexities of distributed systems, security must be integrated from the very design phase, not treated as a separate task to be handled later by a different team just before deployment. A DevSecOps approach is vital here. This philosophy and set of practices integrates security considerations and automated security tools throughout the entire software development lifecycle, from initial planning and coding through building and testing, all the way to deployment and ongoing operations. This ensures that security is a core consideration from the absolute beginning. Vulnerabilities can be identified and remediated early in the cycle, which is far less costly and risky than finding them in production after deployment. This proactive mindset, combined with that multi-layered security strategy we've discussed, encompassing API gateways, MTLS, centralized secrets management, least privilege, builds a robust security foundation that is inherently more resilient to the risks that come with distributed systems. And a snark statistic really highlights why this operational rigor is so important. Some reports suggest that a staggering 40% of cloud security incidents involve simple misconfigurations, humans making mistakes, setting up firewalls, permissions, or other controls. It emphasizes that the human and process elements are often the weakest links, not necessarily the underlying technology itself. DevSecOps aims to catch those mistakes earlier. 7. Real-world lessons. Case studies of major incidents.
Okay, this is where theory really meets reality. We've talked about the immense power and the inherent complexity of microservices, but what happens when things actually go wrong in the real world? It turns out the biggest vulnerabilities, or the root causes of major incidents, aren't always some kind of deep architectural flaw in the microservices themselves. That's a really surprising fact for a lot of people, I think.
Indeed, it's quite humbling, actually. An analysis of major security incidents that have occurred in microservices environments reveals a consistent and frankly recurring pattern. These failures are often not due to inherent architectural flaws in the microservices paradigm itself. They're more often attributable to failures in basic human and operational discipline. Things like critical misconfigurations, inadequate monitoring allowing problems to fester, or poor secret management practices. These are essentially operational shortcomings that get amplified by the distributed nature of the architecture, making them perhaps harder to spot and certainly harder to contain once they occur.
Okay, let's look at one of the most significant and well-publicized examples, the Capital One breach from 2019. This was huge, affecting over 100 million customers. What was the actual root cause of that massive incident? Was it a problem with microservices?
This incident is a classic, almost textbook example of operational failure within a cloud and distributed environment. The Capital One breach was not a result of a flaw in the underlying cloud infrastructure, AWS, or the microservices architecture Capital One was using. Instead, it was a failure to properly configure a key security control. The attacker exploited a misconfigured web application firewall, WF. This specific misconfiguration allowed them to execute a type of attack known as server-side request forgery, or SSRF. This attack essentially allowed the attacker to trick the WAF into acting as a proxy, making requests on their behalf to internal, non-public endpoints. Critically, this gained them access to temporary security credentials.
So the keys to the kingdom, essentially.
Well, keys to a part of it. With these newly acquired credentials, the attacker was then able to access and exfiltrate sensitive customer data from a separate AWS S3 bucket that was also misconfigured with overly permissive access controls. So it was a chain of misconfigurations.
What does this teach you about managing these complex systems? It really seems like it underscores the critical importance of the human element, even in a world of highly automated cloud systems.
This is a powerful testament to the very real risks of human error and the absolute critical importance of meticulous configuration management in cloud and distributed environments. It serves as a stark reminder of that shared responsibility model in cloud computing we touched on. In this model, the cloud provider, like AWS, is responsible for the security of the cloud, the physical data centers, the core network infrastructure, the hypervisor, etc. But the customer, in this case, Capital One, is responsible for security in the cloud, meaning how they configure their applications, their databases, their network access controls, and their security tools like waifs and S3 bucket permissions within that cloud infrastructure. A single human-made misconfiguration, even if seemingly minor at the time, can have absolutely catastrophic consequences in a complex, distributed system. It underscores the absolute necessity of continuous security audits, rigorous configuration management practices, automated checks, and robust change control processes to find and plug these potential security holes before an attacker does. The technology itself wasn't flawed, the human setup and oversight were.
Okay, let's look at another incredibly high-profile incident, the Uber breach in 2022. How did that one unfold? It sounds like it started with a very familiar, almost low-tech tactic.
It did. The 2022 Uber breach began with a very common and often insidiously effective attack vector, a social engineering attack targeting an employee. The attacker apparently first purchased stolen login credentials belonging to an Uber employee from the dark web. These credentials alone weren't enough due to multi-factor authentication, MFA, so the attacker then attempted to overcome the MFA protection. They did this by sending a relentless flood of MFA push notifications to the employee's phone, a tactic now widely known as MFA fatigue. The idea is to annoy or overwhelm the user into eventually accepting a prompt just to make the notification stop.
Just wearing them down.
Exactly. Under pressure and likely sheer annoyance, the employee eventually approved one of these MFA requests, which tragically granted the attacker the initial network access they needed to get inside Uber's internal systems.
And then, once the attacker was inside, it got even worse, didn't it? It feels like the subsequent discovery of internal security vulnerabilities just compounded that initial breach dramatically.
It absolutely did. Once the attacker gained that initial foothold inside Uber's intranet, they began to explore, looking for ways to escalate their privileges. Shockingly, they found a PowerShell script somewhere on a network share that contained hard-coded administrative credentials for the company's Privileged Access Management, or PM, solution.
Wow. Hard-coded admin credentials in a script.
Yes. The discovery of these hard-coded credentials was widely described in security circles as an embarrassing cybersecurity blunder, and it significantly increased the severity of the breach. These credentials essentially gave the attacker the highest level of administrative access to many sensitive internal services, data stores, and potentially code repositories, vastly expanding the scope of their access and allowing wide lateral movement within Uber's systems.
Here's where it gets really interesting for our discussion. Again, this wasn't necessarily an architectural flaw in how Uber's microservices communicate, was it? It was a fundamental security misstep, that hard coding, which was then amplified by the interconnected, distributed nature of their architecture.
Precisely. This incident powerfully illustrates two key things. First, that the weakest link in any complex system, whether it's monolithic or microservices-based, is often the human one susceptible to social engineering or making operational mistakes. Second, it unequivocally demonstrates the critical importance of following basic secret management best practices. Hard-coding credentials is a severe security flaw in any context, but its potential impact is amplified in a microservices environment. Why? Because the compromise of just one service or even one developer's poorly secured script can potentially provide the keys to the entire distributed kingdom, allowing attackers to move laterally and cause extensive damage. It's a vivid, painful lesson in why the principle of least privilege and using centralized secret management tools are absolutely non-negotiable. It's not just about building secure services, but also about establishing and enforcing secure operational practices around them.
And these aren't just isolated incidents happening to Capital One and Uber, are they? It seems like they're really symptoms of a broader pattern in the industry as organizations move to more complex, distributed cloud systems.
Far from it. These high-profile breaches are indeed symptoms of a broader industry trend. Security reports consistently indicate that major companies, even tech giants like Microsoft, face a record number of vulnerabilities year after year. And there's a noticeable shift. Significant rise in attacks specifically targeting digital identity, like stolen credentials, and privileged access rather than just exploiting traditional software flaws like buffer overflows. The distributed nature of microservices, while offering those architectural benefits we discussed, inherently creates a wider attack surface and simply more potential entry points for malicious actors to probe and exploit. It's a clear indication that while the architectural methods for building microservices are maturing, the corresponding security standards, tooling, and operational models for effectively securing them at scale are still very much in active development and require more dedicated research and the adoption of rigorous frameworks like DevSecOps.
Maybe let's quickly highlight a few other real-world examples, not just security, but illustrating the diverse challenges, operational, performance, complexity, that organizations have faced when dealing with microservices at scale. It shows it's not just about security threats.
Good idea. It paints a broader picture.
We had Uber's scaling overload issue, actually reported between 2016 and 2018, even before the breach we discussed. They reached a point with an astonishing 2,200 microservices where basic error tracing became almost impossible. Engineers reported having to sift through logs and metrics from 50 or more different services just to diagnose a single user-facing incident. This caused significant delays and frequent outages.
Wow, 2,200 services.
Yeah, the core lesson there. A highly decoupled design absolutely needs incredibly strong observability, a centralized logging, tracing, metrics. Otherwise, it just becomes an unmanageable mess. Uber apparently mitigated this later by adopting a strategy called Domain-Oriented Microservices Architecture, or DOMA, to group related services logically and improve their visibility.
Makes sense. Grouping helps manage the complexity.
Then there was the DoorDash cascading outage in May 2022. A seemingly localized database latency spike in one core service triggered a chain reaction of timeouts and resource exhaustion across numerous dependent services downstream. This led to widespread downtime, impacting order processing for hours.
The House of Cards effect.
Exactly. The crucial lesson is that you absolutely must build your systems to handle these kinds of cascading failures proactively. You need things like circuit breakers, bulkheads, maybe even global load shedding solutions. DoorDash apparently adopted the open-source Aperture project for this to manage system overload gracefully and prevent the entire system from collapsing due to one bottleneck.
You need resilience patterns baked in everywhere.
In Carbon Health, a healthcare tech company, documented their experience with what they call decomposition bugs between 2021 and 2025 during their ambitious monolith to microservices migration. They publicly reported 107 significant incidents directly related to the migration, including basic refactoring errors, introducing bugs, complex data migration issues leading to data inconsistencies, and major problems with eventual consistency causing null pointer exceptions and other failures.
Migrations are hard. Really hard.
That's the lesson. Migrating from a monolith is inherently risky and complex. It's often wise to consider maybe a modular monolith, breaking up the monolith internally first as a less disruptive step before attempting a full Big Bang microservices leap. Don't underestimate the complexity and risk of the transition process itself.
Good advice. Incremental steps.
Twitter, now X, famously faced API fragmentation back in the early 2010s. After migrating key parts of their system to around 14 core microservices, their public API became disjointed, inconsistent, and difficult for developers, both internal and external, to use effectively. This actually slowed down feature development.
The external view became messy.
Right. The lesson here is the critical importance of careful management of API contracts, versioning, and potentially having a unified gateway or facade layer to present a consistent view over your internal services. Twitter eventually resolved much of this complexity by adopting GraphQL, which provides a unified query language for accessing data across multiple services.
A common pattern now using GraphQL gateways.
And finally, Lyft reported experiencing a noticeable productivity dip around 2018, shortly after a major migration to hundreds of microservices. Their engineers reported severe inefficiencies in their local development and testing workflows. Just debugging and iterating on the code for a single service became cumbersome and slow, bogging them down and reducing overall engineering output for a period.
Interesting. The local dev experience suffered.
Exactly, the lesson. You need to invest heavily in automated inner-loop development tools, local testing environments like Docker Compose setups or tools like telepresence, and fast feedback cycles that allow developers to quickly test and iterate on their individual services without waiting for slow, complex, full integration environments. Developer experience is key.
So what's fascinating here, spanning all these diverse examples from major security breaches like Capital One and Uber to operational struggles like DoorDash's outage or Lyft's productivity dip, is this ongoing debate in the industry. Are microservices inherently complex, almost destined to breed these kinds of problems at scale? Or do these widespread issues stem primarily from implementation missteps, a lack of the right tooling, or maybe just a lack of organizational maturity required to adopt the architecture successfully. Regardless of where you personally land in that debate, these incidents consistently reveal that a significant proportion, some studies suggest, up to 70% of the issues encountered in microservices environments often stem from operational gaps, monitoring deficiencies, or process failures, not necessarily a fundamental flaw in the core concept of distributed services itself. It often seems to be less about the architecture and more about the execution and operation. 8. Strategic recommendations and pragmatic wisdom.
So putting this all together, what does this all mean for you, the listener? Whether you're perhaps considering microservices for your next project, or maybe you're already knee-deep in the complexities of managing a distributed system, it's crystal clear that this isn't just a simple technical migration. It's a profound journey, really, with significant implications for your entire organization, technology, process, and culture.
It's absolutely true. A successful microservices transformation isn't just about adopting new technologies like containers and service meshes. It's really a holistic organizational transformation. It demands a mature organizational culture that embraces autonomy and ownership, meticulous operational discipline backed by strong automation, and crucially, that proactive security by design mindset woven into everything. Our analysis of these incidents consistently shows that the primary vulnerabilities and failure modes in these distributed systems often stem from those human and operational failures, like critical misconfigurations, failing to patch systems, or not adhering to basic security best practices rather than inherent flaws in the microservices architecture itself. The Capital One and Uber breaches serve as incredibly powerful, maybe even sobering cautionary tales that underscore these points vividly.
So if you're taking notes, we're just trying to internalize the key takeaways. What are the core strategic recommendations that everyone involved with microservices should keep front and center? What are the absolute must-dos to maximize the benefits while minimizing the risks?
Okay, based on everything we've discussed, here are a few key recommendations. First, embrace domain-driven design, DDD, from the start. Don't just break things up arbitrarily. Structure your microservices around specific, well-understood business capabilities and use those clearly defined, bounded contexts we talked about. This isn't just about technical decomposition. It ensures clear ownership, reduces coupling based on business logic, and promotes better collaboration between development teams and the business units they serve. Build modularity from a business perspective first.
Makes sense. Align tech with business domains.
Second, invest heavily in operational maturity. This architecture simply demands robust tooling and extensive automation to manage its inherent complexity effectively. You absolutely must invest in modern CI/CD pipelines, container orchestration platforms like Kubernetes, and sophisticated centralized monitoring, logging, and tracing tools. Without these foundational pieces, trying to manage a distributed system at scale quickly becomes untenable, turning your intended advantage into an operational nightmare. Don't skimp on the ops tooling.
Got it. Tooling is non-negotiable.
Third, adopt a security by design mindset. Security cannot be an afterthought tacked on at the end. It must be integrated into every single stage of the development lifecycle. Implement a multi-layered security strategy right from the beginning. This includes the strategic use of an API gateway as a central security enforcer, mandating mutual TLS, MTLS, for all sensitive inter-service communication, and implementing a robust, centralized secrets management solution to eliminate those dangerous hard-coded credentials. Build security in. Don't try to bolt it on later when it's much harder and less effective.
Bake security in from day one.
Fourth, prioritize and enforce the principle of least privilege. Strictly enforce this fundamental security tenet for every single service and every single user account interacting with your system. Ensure that they are granted only the absolute minimum privileges necessary to perform their specific required function and nothing more. This dramatically limits the potential blast radius if any single component or credential is ever compromised. It's about minimizing the impact when, not if, something inevitably goes wrong.
Containment by default.
And finally, perhaps most importantly, maintain pragmatism. Microservices are not a silver bullet solution for every problem or every organization. For simpler projects, smaller teams, or startups just getting going, the significant overhead in terms of tooling, operational complexity, and required expertise introduced by microservices may far outweigh the potential benefits like independent scaling or deployment. A successful strategy might involve a hybrid approach, keeping some parts monolithic while building new features as services, Or it might even involve a thoughtful, deliberate decision to retain a well-structured monolithic architecture where it genuinely makes the most sense for your specific context, scale, and team capabilities. It's about choosing the right tool for the right job, not blindly following a trend or industry hype cycle. Be realistic about the costs versus the benefits for your situation.
That's really important advice. Don't just jump on the bandwagon. Okay, we've taken quite the journey today, haven't we? From exploring the limitations of the monolithic past to dissecting the immense promises and also the often hidden perils of the microservices future. We've seen how this architectural style, when implemented correctly with the right foundations, can unlock tremendous business value, driving scalability, resilience, and agility that monoliths often struggle with. But we've also learned through some tough, real-world examples how it demands incredible discipline in operations, a mature organizational culture ready for autonomy, and especially a vigilant, proactive approach to security at every layer.
Yeah, and if we connect this to the bigger picture, the future of software architecture isn't really about endlessly debating monolith versus microservices as some kind of simplistic either black and white choice. It's fundamentally about learning how to effectively design, build, operate, and secure distributed systems in general, because that's increasingly the world we live in.
Okay.
The inherent challenge for modern organizations, and maybe for you as a learner, a builder, or a manager in this space, is to strategically leverage the undeniable benefits of a modular distributed architecture while meticulously mitigating its inherent complexities. And that mitigation, as we've seen, comes through a powerful combination of advanced tooling, mature and well-understood processes, and perhaps most importantly, a vigilant security-first culture that explicitly recognizes the human element as a critical factor in every success story and every failure.
Okay, so here's a final provocative thought for you, our listener, to mull over as you go about your day, interacting with all the complex software systems around you. Considering all the trade-offs we've discussed today and the pervasive role of the human element, misconfigurations, operational errors, security oversights in so many of these high-profile failures, what single aspect of building or securing complex distributed systems do you think is most underestimated or perhaps underinvested in the tech world today? Is it the sheer cognitive load on developers? The fundamental cultural shift required for teams to truly own their services? The difficulty of achieving robust observability? Or maybe something else entirely, something to think about. Thank you so much for joining us on this deep dive into the world of microservices. We really hope you feel much more informed, maybe a little bit wiser, and better equipped to navigate the fascinating, powerful, and sometimes treacherous landscape of modern software architecture.